Hello and everybody, welcome back to our calculus section. Today we will be talking about u-substitution, or what is known as the reverse chain rule. So the familiar term is actually u-substitution in calculus. I call it the aka reverse chain rule because that's what it really is. Okay, we're trying to solve for antiderivative, and I want to know what does it look like if I use the chain rule going backwards. So here in our first part, we're going to go ahead and recall the chain rule, which says that if f of x is equal to this function over here, then according to the chain rule, f prime is going to be just take the derivative as is. So 1 over 2 times the square root of sine of x, and then we multiply by cosine of x because the derivative of sine is going to be cosine. Well, I want to now take this and apply it to this whole antiderivative that I've been doing. So here is an example of that. Let's say I want to solve for the antiderivative of 2x times x squared plus 1 raised to the 100th power. Now, in the previous section, we can say, okay, well, why don't we just go ahead and expand x squared plus 1 raised to the 100? If you do that, you are going to be in for hurting because there are going to be 101 terms, and then you're going to have to multiply by 2x, and well, you get the idea. That's going to be nasty. So there must be an easier way. So here, I like to think of it this way, okay? Look at the inside right here, x squared plus 1. Now, if I were to think about chain rule, taking the derivative, normally if I take the derivative, then that means that the x squared plus 1, we're going to produce the chain rule, which will give us the 2x, and that is what's over here. So if you were able to kind of, connect the two together, I'm going to say the following then. The antiderivative would then be x squared plus 1 raised to the 101 power, because that's really just the power rule. Now, normally it would produce the 2x, but in this case, the 2x over here and the dx right here, that's where the chain rule comes in. As a final part, I would say then also, according to the power rule going backward, I'm going to go ahead and divide by 101, and then we're going to say plus c, and that right there is then our antiderivative. Now, if you can see all of that, that's great. But for those of you guys that can't see it, let's take this one step at a time so you can see what's actually happening. Integral of 2x times x squared plus 1 raised to the 100th power dx. Now, just like the chain rule, here's what I'm going to do. I'm going to go ahead and say let u, the inner function, be the inside, x squared plus 1. So then now we can go ahead and solve for the derivative of that. So du is equal to 2x dx. Okay, just taking the derivative of both sides. Normally, again, I would write du over dx, but in this case, I think du is equal to 2x dx might be a little bit better. Let's go back to our integral right here, and let's go ahead and replace everything in terms of u. So the first part, we'll notice that the x squared plus 1 raised to the 100th power, that is going to be u to the 100th power, okay, because u is the inside function. The du right here gets replaced by 2x dx, and you have that right there, 2x dx. So that is going to be du, and then we have an integral. Notice now what we did was we took something that was really nasty that we couldn't figure out how to solve for and changed it into something very simple where you can see that it's just really the power rule. So, as we said, take the antiderivative of u to the 100. So that's going to be u to the 101 divided by 101 and then plus c. And then the final item is that I'm going to go ahead and replace u back with its original function of x squared plus 1. So my antiderivative is 1 divided by 101 times x squared plus 1 raised to the 101 power and then plus c, just like we said earlier over there. So that's the idea of this u-substitution. It's really just the chain rule going backward. And I'm going to go ahead and use this u-substitution because, again, not everybody can see that jump that I did in the first example. All right, so here we go. Let's look at this case right here. Cosine of 3x plus 2, and then I want to take the antiderivative of that. So just like before, what we're going to do is we're going to go ahead and identify the inner function, which is 3x plus 2. We're going to go ahead and call that u. So u is equal to 3x plus 2. And so du is equal to 3 times dx. Don't forget the dx part on the right-hand side because that is important. Okay, so let's see here. I noticed that in my original equation, if I were to rewrite everything in terms of u, we're going to have cosine of u. Now, this part of the dx, well, that's a problem because I need to solve for that. Well, we just have to take that second step and extend it a little bit further. If du is equal to 3 times dx, then I believe dx is equal to du over 3. So that is going to be what gets replaced by dx then. So du over 3 goes over here. The 1/3 I can take it outside because I think that might look a little bit easier to deal with. And the inside is still just going to be cosine of u du. What's the antiderivative of cosine? Well, that's just going to be sine then. So then that gives me now 1 over 3 times the sine of u plus c. Always don't forget the constant. And now we're going to go ahead and replace u back with its original function. So the antiderivative is 1/3 times the sine of 3x plus 2, and then we have the plus c in the end. Okay? All right, let's look at a few more. This time, not so obvious over here. What is the antiderivative of tangent of x? Well, remember, this u substitution, we need to be able to see the inner function and also the inner function's derivative in order to use this reverse chain rule. So what I'm going to do is I'm going to go ahead and take this tangent and rewrite it as sine of x over cosine of x dx. Now, at this point, you have two options. You can either use option number 1, which says that u is equal to sine of x. And then option number 2, which is going to be let u equal to cosine of x, because it's not that obvious as to which one's which in this case. Well, if we were to just go through each option just to see what happens, in option number 1, du would then be equal to cosine of x dx, whereas option number 2, du would then be equal to sine of x dx. I'm looking at option number 1 right there. That unfortunately is not viable because we don't have cosine of x times dx over here. Rather, we have sine of x times dx over here. So what that tells me is option number 2 is probably the way to go. If you ever have to choose between the numerator and the denominator as an inner function, I think the denominator is probably the best choice. Okay, so that's going to be my option right there. So now let's go ahead and go back. So this is now going to say integral sine of x dx, that's going to be du, so that goes on top, divided by cosine of x, well that's just u, and that goes on the bottom. If you need to see it a little bit better, maybe we can write this as 1 over u times du, and that we definitely do know the antiderivative of. So that's going to be equal to the ln of absolute value of u, don't forget the absolute value now, and then plus c. So now we replace back with what we have. So ln of absolute value of u is supposed to be cosine of x, right? And then we have the plus c there. Okay? All right. Now, let's go ahead and move on. Actually, you know what? There is something I want to mention. This is kind of like a really special case though right here. Here's why. Normally, we would say plus c for the antiderivative. But you can go a little bit further and say the following. The antiderivative could technically be ln of absolute value of u plus ln of c instead of just say plus c. Ln of c is still a constant, so you're still adding a constant to the antiderivative, which is fine. But the reason why would I want to do this instead of just saying plus c is because ln of absolute value of u plus ln of c, I can write that as ln of absolute value of c times u. So what that means is that another form of the antiderivative is ln of absolute value of c multiplied by the cosine of x. Notice now the constant is inside, which is not wrong. This is just another variation of the antiderivative. So that is something that we're going to see in the near future. So just kind of keep that in mind. Okay. Now let's go ahead and look at some sort of definite integral with this u substitution. Okay, the u substitution with this definite integral is actually pretty easy in this case, even easier than the indefinite integral. Okay, so antiderivative or area under the curve of 0 to pi over 2 of that function cosine of x times sine of x dx. I think it's pretty clear in this case that my inner function is going to be sine of x, and my outer function is going to be sine in this case. Well, let's go ahead and write that on the side. So u is equal to sine of x, and so du is equal to the cosine of x dx. Now, before we go on, let's just make sure that matches. Cosine of x dx, I definitely do have that in my equation, so that means we are going on the right track. So let's go ahead and replace everything in terms of u then. The first part, this right here, that is just going to be the sine of u. Then the second part, cosine of x dx right here, that is going to be the du right there. The integral, now this is where you have to be careful. You changed everything from x to u, so that means your boundaries should also change as well. 0 right here, in terms of what it becomes, remember when x is equal to 0, then what is u equal to? Well, that's where we're going to go to my substitution over here. If x is equal to 0, according to my u substitution, then u is equal to sine of 0, which is equal to 0. So my lower bound still is 0, so that's not a problem. But my upper bound, if I use this substitution, if x is equal to pi over 2, then u is equal to sine of pi over 2, which is equal to 1. So that's going to be my upper bound right there. So notice how, again, because you changed it from x to u, that's why you have to change the boundary. So let's go ahead and take the antiderivative. So the antiderivative of this is going to be cosine of u negative, right? Because again, it's antiderivative. Boundary from 0 to 1. Now, normally, we would go back and change u back into in terms of sine of x. But in this case, we don't have to, because all we have to do now is just solve for this by using FTC2. We can literally just plug it in. Why go back to x and change my boundaries back to what it was when I already did it, right? Because, we don't want to make some extra algebra work. So what I'm saying now is just literally plug it in. So negative cosine of 1 minus negative cosine of 0. So that's going to give me negative cosine of 1 and then plus cosine of 0. And that comes out to be negative cosine of 1, which we don't know what the numerical value is because I don't have a calculator, and then plus 1. And that's going to be my antiderivative then. So when it comes to definite integral and this u substitution, just remember to make sure you change the boundary. And once you take the antiderivative, plug in the boundaries, and that's it. You don't have to change it back to x. Okay, let's take one last example over here, right? 1 over 3, from 1 to 3 of x divided by 1 plus x squared. By the way, if you want to try this on yourself by yourself before we move on, we can go ahead and do so. Pause the video and then try it. And then if you're done, then you can go ahead and unpause it. All right, so let's just say we're unpaused already. I'm going to go ahead and say u is equal to 1 plus x squared because earlier we said, hey, the denominator is probably a good place to start as a u substitution. Du, in this case, is going to be 2x dx, which we kind of have. The important part is that we have the x dx because I see that in our equation. The 2, we can just move it over to the other side. So then that means that the x dx in the equation is the same thing as du over 2, and that's what our replacement is going to be. Let's go ahead and change everything in terms of u. So my boundary used to be 1. X used to be 1. If I plug x is equal to 1 into my u substitution, then u is equal to 1 plus 1 squared, which is equal to 2. So my lower bound is now 2. But whereas for the upper bound, x is equal to 3, and if I plug it in, u is equal to 1 plus 3 squared, which is equal to 10. So that's going to be my upper bound. My x dx, as I said earlier, gets replaced by du divided by 2, multiplied by the bottom part, 1 plus x squared, so that's just 1 over u. Okay, let's clean this up a little bit more. We'll go ahead and put the 1/2 outside. The integral of 1 over u from 2 to 10 du. The antiderivative of 1 over u, we said, is going to be the ln, absolute value of u. The 1/2 carries over. Boundaries from 2 to 10. Again, don't change it back to x, just literally plug in what we have. Okay, so 1/2 multiplied by the ln of 10, and then for the other part is going to be minus 1/2 multiplied by the ln of 2. And note that I didn't put the absolute value because 10 and 2 are positive, so I mean it's just still going to stay the same if it's absolute value. Final item, maybe we can go ahead and factor out the 1/2, and our final answer would then be ln of 10 minus the ln of 2. Or if you want, do a little bit of fancy algebra, which I think is good because you might see this on multiple choice, is ln of 10 divided by 2, which, looks like a lot nicer. It's going to be ln of 5 in this case then. Okay, so there's going to be your area under the curve. All right, so I think that'll do it. Thank you so much for watching. I will see you guys next time. Okay, goodbye.